This is a photo of what they call muskegs in Northwest Territories. So it's patches of wetlands with forests. So the story today is the permafrost hydrology. So there are actually some permafrost underneath these muskegs, and so how the water moves around in this landscape is the story. And then I just have a lot of co-authors, mostly my long-time colleague Bill Quinton from Laurier University, and my postdocs students, and also the colleague Larry Bentley, who is sitting here. So I'll just do a quick introduction on the permafrost. Maybe I'll just turn the lights down a bit. So this is the map of permafrost in Canada, taken from the GSC's map, Natural Resources Canada, or the Geological Survey Canada. Now, so the definition is, when you say it simple, it's really simple. So it refers to the ground that's frozen for more than 2 years. And then there are different types of permafrost. For example, if you go to north, you get this continuous permafrost. As the name suggests, it's basically a continuous slab of frozen ground, and typically very thick, sometimes in excess of 200-300 meters. And you go to the southern end of the permafrost region, so you get this discontinuous permafrost. So those are patches of frozen ground placed among the seasonally frozen ground. So there's a gradient of permafrost thickness and distribution. And then what we're talking about today is this discontinuous permafrost. And then this is based on our work that we have been conducting for the last 15 or so years near Fort Simpson, Northwest Territories. So this region has several unique characteristics. One, it's situated in the discontinuous permafrost terrain. Also, it happens to be in the land with a high density of wetlands, i.e. muskegs. So the high density of wetlands, because it's so flat, there's not a whole lot of topographic gradient in this region. So it's pretty much, in terms of geomorphology and geology, the area around Fort Simpson is very similar to the prairies in Saskatchewan, except that it's colder. So for that reason, there's a lot of decomposition of plants and peat deposition, and then you get this high density of wetlands. So this is the area where the story today is going to be applicable. So it's a rather large area encompassing Northwest Territories, a bit of northern Alberta, and then a bit of northern BC. And this happens to be the area where there's a lot of petroleum deposit is located. So one application of the finding of our study is how do we exploit these natural resources in the areas of the lands of the muskeg. And then also this region, the subarctic region of Canada, happens to be the area with one of the fastest warming on the planet. So this is mean annual air temperature measured at the Fort Simpson Airport from the turn of the 20th century till recent. So you can see that there is a significant increase in air temperature from about 60s, 70s to the recent. So the question is, so given that the temperature is going up, how does that change the permafrost distribution? And then this change, how fast will this change occur? And then how will this change impact the water cycle, for example, river flow? And so that has a relevance to the water supply for the First Nations communities, and also water supply for the resource extraction and development. So by understanding the permafrost hydrology in the muskeg lands, we're probably able to provide a scientific basis for the adaptation to climate change in this region. So that's the big goal that we're working towards in this study. So back to this muskeg land. So this has a very complex vegetation distribution. So you got this forest. It's a black spruce forest. It's not really impressive tree. It's only about 4 or 5 meters high, and the canopy is rather sparse. So these trees grow only on the land that has a permafrost core. So you can tell by just looking at the trees. So there's a permafrost here, permafrost all over, and then there's no permafrost in these regions. So this forested area is raised by a meter or so with respect to the surrounding wetlands. So we call it the Peat Plateau. And then there are two types of wetlands, generally speaking. There are some bogs. These are bogs with a flat surface. And then it's actually a bit lower than the Peat Plateau, so that's called a flat bog. And then there are channel fen. So these are different types of wetlands. And I'll show you pictures of these two types of wetlands in a minute. And there are snowmelt runoff and the rainfall runoff occurring from the Peat Plateau to the bogs and fens. But this runoff coming from Peat Plateau doesn't have a lot of nutrients because this is a nutrient poor area. So that there's not a whole lot of nutrients to support the plant growth in the bogs. But then in channel fens, these are located in the main drainage pathways. So it actually receives the nutrient inputs from upstream regions. So there's some lakes upstream, so that carries nutrient, relatively speaking, nutrient-rich water. So that creates a contrast in vegetation between fen and the bogs. So this is a picture of the Peat Plateau. So it supports the vegetation, the black spruce growth. And then these are two types of wetlands. So this is channel fen. So it's got relatively nutrient-rich water flowing through. Therefore, it allows the growth of vascular vegetation, such as sedges. Whereas this bog, just about the only thing that grows in the bog is the sphagnum moss. And then acidity of this water in the bog is rather high. So the pH of this water, we're looking at 4.5 to 5. So it's acidic water in the bog and neutral water in the fens. So that shows up in different vegetation. So I'll show the cross-section, schematic cross-section of a Peat Plateau. So it would look like this. Okay, so I'm just drawing a line from fen to bog through the Peat Plateau. So this has a permafrost core, and then there is a thick blanket of peat both on the plateau and also the wetland side. And then here is the, what we call a frost table. So this is hard frozen peat. So there's a very little capacity to allow water to percolate down. So the water actually is piling up above the permafrost, and then this is an expression of water table. So this is a pit. We dug this pit about 50 centimeter into the permafrost. And then so you see this water piling up. And this is a picture of a peat. So I think most of you are familiar with the peat as a growing media. You go to Canadian Tire, you can buy a bag of peat. And then that's just full of air spaces. The porosity of peat is running up at about 90%. So it's just lots of air with a bit of organic material. That's what the peat is. So it's really soft like sponge. And then for those of you who are somewhat involved in Arctic research, this is the White River ash, about 1200 years AD. So there's only about this much of a deposition of peat since 1200 years. But nevertheless, so this is mostly peat. And so that becomes an important point when I talk about the hydrology of this Muskeg region. So this shape of the permafrost table is quite important because it controls how the water gets drained from the Peat Plateau to wetlands. So we do an annual transect survey of this frost table along this 40-meter transect. So what we do is we go out with this a metal stick about 1.5 meters long with a pointed end. So we just stick the stick into the ground and you hit the permafrost. We know the permafrost is 20 centimeter down or 25 centimeter down. So this is a result of a survey from 2006. So GS stands for the ground surface. So this was measured using the optical level. And then this is a frost table. So you see that the frost table actually resembles the shape of the ground surface. But if you look at it closely, the frost table is deep in some places and shallow in some other places. And so this depth distribution, half meter here and almost meter here, turns out to be non-random. So you go out in different years, you still see the deeper frost table in the same spot. So this is the result from 2009. Ground surface has subsided a little bit because ice has a higher volume compared to liquid water. So when the ice melts, it causes the subsidence of the ground. And this is the frost table. So here is a place where we couldn't reach with this frost probe. So we want to know why frost table is deep in where it is deep. So it turns out it's related to what we call heat conduction. Okay, so there are a couple of equations I'm going to show in the next slide, but bear with me. So this is how the heat conduction works in principle. So there's a ground surface. It's warmer compared to this frozen peat. So that's the distance from the ground surface to the frozen peat. I just use Z as a depth. And then this is the heat conduction flux. So there's a heat flowing from the warm ground surface to the cold frost table. Temperature of ground surface is Ts. The temperature of frost table is 0 by definition. And then this is how we write a mathematical equation of heat conduction. The amount of heat flowing from the ground surface to the frost table is equal to the temperature difference divided by the depth to the frost table. And then, so this is a coefficient. It's called the thermal conductivity. Now, when we have this peat covering the ground, the thermal conductivity is variable, actually quite a bit variable, depending on how much water is in the peat. Remember, peat is this fluffy material, 90% porosity. And then, so if you have a dry peat, it's actually a good insulator. It's like your fiberglass insulation for the home. But when you have a wet peat, it actually conducts heat reasonably well. So there is a change in heat conduction from relatively dry to completely wet state. So what this tells us is that wet peat, more heat flow, dry peat, less heat flow. So when you have a wet peat, the thawing of permafrost is faster. When you have a dry peat, thawing is slower. So we want to test this hypothesis, so we put what we call soil moisture sensors and soil temperature sensors in the pit and 2 locations. This is what we call a center pit, and that's west pit. And then, so we measured the frost table using a frost probe at the center pit and the west pit. Okay, I'm just going to go back here. So center pit is located in a place where the frost table is deeper, and the west pit is where the frost table is shallower. And this is what we saw in 1 year. And then we put that mathematical equation for the heat conduction with, well, this is something we call a differential equation, just to model how fast frost table is lowering from the heat balance. And then this is what the model predicts, and it matches with the field results. So this is clear indication that there are fundamental differences in thawing rate between this west pit and center pit. And the difference comes from the fact that at the west pit, the peat remains relatively dry throughout the season, whereas the center pit, peat is always wet. Now, so the next question is, why does the peat remain wet in this spot, center pit? So this will have to consider the movement of water in this peat. It's a water kind of flowing sideways, going this way or that way. So we needed to expand our thinking into two-dimensional space. So what we did was we used this, the trusty frost probe, and then we measured the frost table every 25 centimeter in this plot. And then we generated a map of the frost table. So this brown one is a ground surface map, and then this black one underneath is a frost table map. So I will just show you a diagram where I strip off this brown surface, just expose the frost table. So this shape shows the frost table, and then the color shows a result of a model simulation. So we built this groundwater flow model and put 15 millimeter of rain into the peat, and allow this rain to actually soak in and flow sideways following the law of gravity. And then, so this is what you get. The color indicates the thickness of saturated peat. So basically, the purple color indicates the wet region, and it's not hard to imagine because there is a frost table hill, so the water kind of flows down the hill and then end up in these depressions in frost table. So this process of lateral flow of water keeps this deep spot always wet. As a result, the wet spot thaws even deeper, so there's a positive feedback processes. So the wet spot, deeper frost, and deeper frost, more wet. So, and then so that basically creates this positive feedback loop, and then just creates this differential thawing at a small scale. Remember, this is just 5 meter by 5 meter. So we're looking at size of that patch of land. So we think this process at this scale is important, but we want to see how it expands into the bigger scale. And we can't really do this frost table every 25 centimeter in a bigger scale, so we use a different tool. And this is where Dr. Bentley comes in with his electrical resistivity equipment. And what you don't see in this picture is there are hundreds of mosquitoes buzzing around Larry. And I wear a net, and he doesn't. So, so one year, it was summer of 2009. So we went out and then put this line. So electrical resistivity imaging. So basic principle is that you put electrodes, shove the electrodes into the peat every meter or every few meters, depending on the design of the survey, and then shoot the electrical current from dozens of different combinations of electrodes, and then just see the response of ground, how resistive the ground is to electricity. And it's the same principle we use for the medical imaging, the CAT scan and MRI. So we just do it on the ground. And then this is the image we get. So the black dot is the frost table we measure with the frost probe, and then the color shows the resistivity. Basically, the red color shows the highly resistive material, i.e. ice, and the blue color shows wet material. So what we see here is the permafrost in red, and then we have two different materials. So this light blue is unfrozen peat, okay, so about 90% porosity. And then underneath is the clay. So it's a glacial deposit, the same as what we have here in Alberta, Saskatchewan. And then the boundary is about 3 meters. So there's a 3 meter of peat deposit, a thick blanket of peat overlying. And then we want to see the finer details, so we run the same survey with smaller electrode spacing. And then this is what we get. So you have, again, the frost table here. And then you got this a blue color, a little bit deeper frost table, indicating there's some differential thawing here. So on the ground, it looks like this. It's a little wetland. It's a wetland about the size of this table and a bit bigger. So what's happening here is there is a differential thawing due to this positive feedback. It creates a little hole about this big. And over the years, this hole grows and grows to a mini wetland here. And then what we want to know is what happens after this. If we leave this for another several decades, what will happen to this mini wetland? And then we looked at detailed digital elevation map of the area. So this brown is a high elevation, green is a low elevation. But we're talking about elevation difference of about 1 meter. And then you get this little pock marks in this Peat Plateau. And then these are the results of that little mini wetland, getting bigger and bigger over the year. And then you can kind of see where this, two pock marks kind of coalesces each other, and it becomes even bigger wetland. So question is, just going back, so this mini little wetland, there's still permafrost underneath. And then the question is whether there is a permafrost underneath this, wetlands that are visible on this digital elevation model. So that's 100-meter scale bar. So we run geophysics, and then it turns out that is punched through. So there's no permafrost left underneath these little pock marks. So indication here is that there is kind of a gradual evolution of a little hole in the ground to a bigger scale wetlands, and then eventually to more of an open wetland network. And you can see that in the satellite images. So this is an air photo, and we delineated this forested area, i.e. permafrost by green. So that's a 1977 air photo. And then this is 2000. This is from a satellite image. And then 2008, again, from a detailed air photo. So you can see that a green area is shrinking, i.e. the permafrost is shrinking and the wetlands are growing. So the area of Peat Plateau in 1977 photo was about 53%, half permafrost. Now it's kind of diminishing to about 43% in this 2008 image. Now we happen to have our site, this is a detailed study site, located right at the edge of this green and gray, so the edge of wetland and forested permafrost. And then this is what it looked like at our study site. So this is my colleague standing with the device to measure the soil hydraulic property. And then this is our data logger. Okay, so data logger didn't move. It stayed at the same place. So August 2002, this is 2013, just last summer. So you can see that edge of the wetland encroached from here now up to here. So they're probably at 10 or 15 meter of the encroachment of wetland. So this is a kind of confirmation that this shrinkage of permafrost is happening on the ground. Now, so what this tells us is that wetlands are becoming larger and larger in this landscape. And also, wetlands are becoming better connected, so they generate new drainage pathways. So drainage efficiency is increasing in this landscape. Now, so what are the consequences, when we put this picture into a bigger scale? The consequence is this. So this is the data of the river flows monitored by Water Survey of Canada. Some rivers going back to 1970. So these are all near F.Simpson, and the rivers draining this Muskeg land. So not much, well, there's a lot of variability, but not much was happening up to this point. And then around 1995, there seems to be a steady increase with ups and downs of flow. Now, so this unit is a funny unit for river flow. We usually measure river flow in cubic meter per second or cubic feet per second. But I have divided the volumetric river flow by the drainage area. So this is what we call annual yield of river basins. And then the size of the river basin varies from 150 to 1900 kilometers squared. And then these are all showing a similar trend. So this is not the measurement error or some isolated incidents. So it's happening all over the region. And then one might say, well, maybe the rain and snow is increasing in the area. So this is the precipitation record from the F.Simpson Airport. There doesn't seem to be a steady increase in amount of precipitation. So this is happening not because precipitation increased, but something with the drainage mechanism. The plumbing of this Muskeg land is changing. And we think this is related to the permafrost thawing. And would like to understand it better and even make some predictions as to what happens in the next 50 years. This is quite important because they're talking about securing a lot of water resources for the shale gas development in northern BC and things like that. We really need to know how much water is available for the future natural resource development. So I'm going to tell you about some of the modeling efforts that we have started, but I thought I would just take a break and show you some pretty pictures, because I think a lot of speakers for this seminar will have shown you pretty pictures. But I will start with not so pretty pictures, because a lot of people ask me, when I give talks, why did you go to this F.Simpson? Why did you go to this Scotty Creek in this desolate place? So it's just all by coincidence. So this study was actually started as a global effort called the Global Water Energy Experiment, the GEWEX. So there's several nations involved. There are GEWEX sites all over the world. So Canada's contribution for GEWEX was called the Mackenzie GEWEX study, MAGS. So this was initiated in 1995 and ended in 2005. So Canada's role in GEWEX was to understand the hydrology of circumpolar region, so the region that's draining water to the Arctic Ocean, using a Mackenzie Basin as an experimental watershed. And then it's really important in terms of the global circulation, because the amount of fresh water going into the Arctic Ocean determines how much fresh water is actually going out of the Arctic Ocean through the channel between Greenland and Canada. So that's related to this, what the modelers call a thermohaline circulation that regulates the climate of the entire planet. So that was the purpose of Mackenzie GEWEX study, MAGS. And the Scotty Creek study was initiated as one of the MAGS nodes. So there are 1, 2, 3, 4, 5 nodes, and they're representing different kind of physiographic region. Now, so this is very lofty goal of using Mackenzie River as experimental watershed. So, so we got assigned the task to set up something at this F.Simpson region. Now, so this, the huge project, and then what we got as a resource, personnel, Bill and I, only two of us. The budget, $15,000 a year. Now, $15,000 a year seems like a lot of money, but it isn't in the north. So what we did, so we just had a humble beginning. So first year we just, burned all our money on the helicopter. So because, hydrology is really important to know the land and understand what's happening. We had to start from scratch. We had zero knowledge of the hydrology of this site. So we flew around and sometimes landed with some equipment and took some measurement, and I got the idea of how things worked. Actually, I'm 50 years old, and I've been doing this hydrology for all these years. But this week, flying with a helicopter, with Bill, and trying to figuring things out was probably the most productive, time of my entire career, because we had to figure things out from scratch. And then, so we said, okay, this is what we want to do, and then we set up this soil pit with the temperature sensor, moisture sensor, and some weather stations. And then you can kind of see we're recycling some survey tripod, because we couldn't buy the regular tripod. We didn't have money. So that was a humble beginning, and then so we started getting more funding, and then we're now able to actually set up a camp. So it was not very great camp, but we had this the large enough tent to have two of us cook and work on the computer at night. And then, so it was also nice, this was our camp, and then this was our study site. So you just step out of the camp, and then you can measure things right away. And then, so we gradually accumulated equipment for measuring more complicated stuff. And then, around 2006, Bill received some funding to actually build a Camp Scotty 2. So, around this time, helicopter was just eating too much of our budget. So we wanted to move to a place where we can use a float plane, which is much cheaper than a helicopter. So we built this camp. So now we can land with this. This is a beaver those of you who are familiar with this Arctic plains. And then, so we now have life. Okay, so this is Dr. Bentley and Alistair back there, and then Brenda, my student, and this is the helper from the First Nations, and so they're playing crib. And then, more importantly, okay, so now we actually have a washroom with a mosquito net. So that was Camp Scotty 2, and then that served us for a few years. And then my colleague Bill had started taking on more students. So this was getting too small. There were only about 6-7 people max capacity. So we built Camp Scotty 3 in 2012. So this was a much bigger kitchen tent. When we have, at one point, we had 8 sleeping tents around this kitchen tent. Then this was the crew from this past summer, 2013. Now it's kind of good to have infrastructure, but I kind of I'm nostalgic about old days. Now these guys, you get all these young students. What they ask? Internet, Wi-Fi. So we used to have a conversation after dinner, but now what they do is all this, 8 of them sitting and then doing this, and then watching YouTube and all that. But nevertheless, it serves us well. And then because we have more time and more convenience, we can actually enjoy certain things. Like my favorite time, just sipping scotch, just looking at the sunset, off the deck. And sometimes if you wake up in the middle of the night, you can kind of watch something like this. So, so there are some perks to doing work in the Arctic. So now I'm going back to the science here. Okay, so we want to predict how fast permafrost is thawing and how it's impacting the water cycle. So there are a number of people, actually probably a dozen people around the world working on this permafrost modeling. So majority of them, in fact probably all of them, use this approach, which is to look at the vertical energy balance. So you got the sunlight hitting the ground and then warm air heating up the ground. So it's all vertical, moving up or down. And also they use a large grid cell. So their model looks at the tile about 50 kilometer by 50 kilometer because they have to deal with a large area. And then as a result, they assume that there's no sideways movement of water or heat in the landscape. And then you can kind of do some useful things, like this is work done by our colleague at the Canadian Center for Remote Sensing in Ottawa. So he's predicting, okay, so this pink area is where the permafrost is going to disappear by 2090. But if you look at each one of these grid cells, the reality is this. So you got the mix of lake, wetlands, and permafrost peat plateau. And there's a lot of lateral action going on. So we really need to address these processes in order to make a better prediction. And also, when you talk to the people in the native communities, First Nations people, they're not interested in things happening at this scale. This is, okay, permafrost is shrinking, so how does that change the migration pattern of caribou? Or, or we used to be able to trap there, but we can't trap because it's just too wet. And then also how it's impacting infrastructure, roads, and water supply. So you really need to get down to this level to answer that question and then provide useful information for the climate change adaptation. So just demonstrate that point. So this would be permafrost thawing, just looking at this tile as a simple continuous permafrost. And then so you get this vertical thawing, and eventually permafrost thins and disappear one year. But in reality, we got this landscape that's already punctured by the differential thawing of permafrost. So you get this both vertical thawing and lateral thawing, and then this is what happens. So we need to represent this in numerical models and then improve our prediction. So this is what we're doing now. So we start with the field data. We do numerical modeling, but we are always kind of grounded on the field observation. That's the approach we like to take. And then we get the latest model. So this is a model developed by the Center for Remote Sensing. So it's a computer code to look at how the sun is coming through the canopies of the tree, and then how the sun is warming up the canopy, and the canopy warmed up, and then now it's shooting the heat down to the ground. And all those complex processes modeled by this NEST model. And we combine this above the ground model with this below the ground model of heat conduction through the peat and the clay. And then this is the preliminary results. So we want to simulate the thawing, the lens of permafrost that we identified with the geophysical imaging. And then this is how it was in 2004. And then we run the simulation for 6 years. And this is how it is in 2010. So there's both vertical and lateral thawing. So vertical about 1.5 meter, and then lateral 3.5 meter from one direction. It's actually 7 meter if you think about the both direction. So it's a lot more thawing laterally than vertically. So this gives us a grasp of how we model the thawing of a naturally induced permafrost thawing. And then, so if you run that simulation for 20 more years, and by 2032, there's not a whole lot of permafrost left. So this permafrost is kind of counting. In about 2 decades, they're all gone. Now, so that's natural thawing. And there's actually something that's induced by the human activities on top of climate warming. So this is a natural drainage pathway of the Scotty Creek watershed. That's a 150 kilometer squared watershed. It's rather small watershed. And there are some lakes, and then there's a main stem of Scotty Creek, and then tributary there. There's a lot of water movement in these areas, but that's all through the complex network of wetlands. And then, so you fly over, you notice something, this linear features. So there's a seismic exploration back in the 60s. So they basically cut the trees and opened up the canopy. And you got this straight line going through the peat plateaus, and then sometimes connecting lakes and wetlands. So there's a crisscrossing network. And then on the ground, it looks like this. So what they have created is basically the network of drainage ditches. So this would probably impact the flow of water coming from this watershed. So we want to see how this removal of canopy by seismic exploration would impact the permafrost thawing. So we, again, look at the data. So this is an air photo image that I showed you a few minutes ago, so from 2008. So you see this feature that's snaking around the ground. So actually, this is a winter road. This was built about 40 years ago. And then, so it looks like this. So, the canopy is removed. So now you have this linear bogs going through the canopy. And then, so that's the elevation map. So we run geophysics perpendicular to this winter road. And then this is what we saw. So again, permafrost, high resistivity in red. And then this is not thawed yet. So we can actually probe the frost table with our frost probe. But the resistivity is much lower than this permafrost, meaning there's some liquid water there underneath. So it's a partial thawing feature. So we want to see if we can model this. So we use the same approach. So using this complex model of energy transfer through the canopy, and combine that with the subsurface heat conduction model. And then run it from 1969, when the winter road was put, the canopy was removed. All of a sudden, the sun is hitting the ground. And then we got the thawing by 2010 of 2 meters. So that matches with our geophysics results, showing a few meters of thawing. And then permafrost is still intact, underneath. And then we thought we'll just run it for a few more decades. Okay, so this is a 2010 simulation results, and then you go from 2010 to 2030 and 2050. So And there's a gradual thawing of permafrost, and this is probably going to disappear by 2100. So what our field studies and modeling have shown is this. This is almost getting to the end of my seminar here. So we have this Peat Plateau that has a permafrost core. So that's been there for maybe several hundred years. And then, for some reason, either naturally or artificially, the canopy thins. And all of a sudden, you got increased radiation input, solar radiation input to the ground. So that creates a differential thaw, a little bit more thaw underneath the open canopy. But then you got this water piling up into these depressions that you've created. So that initiates the positive feedback process. So that accelerates the thawing. So you basically created a runaway thawing of permafrost. So eventually, you got this new bog forming. The permafrost is punched through. And then so this bog is going to grow to merge with other bogs. And then you basically create a new drainage pathways. And then this same thing could be created by putting seismic lines. So the take-home messages from this talk is that the open canopy and wet conditions is conducive to differential thawing of permafrost. And then the thawing can affect the wetness of the land and also cause a dramatic shift in the water cycle. That might actually change the river flow regime when this occurs over a large scale. And then resource exploration activity can have a strong influence on these processes. So we need to think about this when we think about adaptation to climate change and how we can better manage the resources and how we can better explore and extract natural resources. And then I have this acknowledgement to all these people. There's just a few. There are lots more people who have helped us over the last 14 years of study. And then particularly this native guide, Alan Bonnet-Rouge. He was really fun to have in the field. And then funding, we got funding from International Polar Year, Canadian Space Agency, and then Foundation of Climate, Atmospheric Sciences, and NSERC. And then we couldn't do our work without the collaboration with the First Nations and also the Northwest Territories government. Well, thank you for your attention. I'll be happy to answer any questions. Yes? Oh, this one. Yes, that's a very good point. So we did not want to use the climate warming scenario at this stage. So we just repeated 2000 to 2010 temperature. So the same decade, multiple times. So basically what we're saying is that temperature stays at the same level as now, which is quite a bit higher than it was 100 years ago. Yes, it is very conservative.
Did you have any indication of how long the permafrost had been in your sample zone? You said it was greater than 2 years, but do you have any information?
Yeah, that's a very good question. So, it's sort of like speculation at this point, but the current extent of permafrost is kind of carried over from the Little Ice Age. So the permafrost extent and depth probably was maximum around early 1800 or mid 1800, and then it's shrinking. But I think this permafrost we're seeing has been intact at least for the last couple of hundred years, even more. So I can't really say anything beyond 1,000 years or so. Yes.
Masaki, do you consider albedo changes in your model at all? Mm-hmm.
Yeah, that's all taken into consideration. But there's a large change in albedo between water surface and the vegetation. But among the vegetation, we actually did bring out our albedo meter and the measured albedo. So changes are, say, 0.2 to 0.15 or 0.25 to 0.2, so it's relatively small. But then when you turn it into water, there's a huge change. Yes?
Masaki, at the beginning of your talk, you said that the water chemistry was different, that the peats were much more acidic.
Mm-hmm.
Do you have any ideas with the runoff increasing, is that runoff going into the rivers more acid and affecting the environment that way?
Doesn't appear to be so, because this water flowing through the main channel is largely carried through the network of fens. So there is some buffering mechanism there and also there's a little input, not very much, but small input of groundwater through this glacial till that carries a lot of carbonate, dissolved carbonate in. So there doesn't appear to be a lot of impacts on water chemistry, but there are some concerns about increased level of mercury and things like that, as the peat thaws and methyl mercury is released. But we're not really looking at that at the moment, but there are some concerns. Oh, yes?
I'm just curious, I guess from working in some of the Arctic areas, they talk a lot about the impact of land fragmentation. It's usually what you've talked about, the seismic
Right.
lines, the roads, and then how that affects ecosystems. Can you see a way of kind of combining a lot of that work on fragmentation and ecosystems with what you're doing really on water and this energy cycle?
Yeah, very much so. We used to strictly look at hydrology because Bill and I were both hydrologists and we started this work. But 2 years ago, we decided to bring in ecologists, and then that's why we had to build that Scotty Camp 3. So what they're doing is it's unbelievable. They're measuring the tree trunk, I guess, of every single tree that has a diameter bigger than 10 centimeter. So they're talking about tens of thousands of trees measured over the next 2 or 3 years. So definitely the idea is to tie in ecology with hydrology. We don't have animal people working with us right now, but that's probably on the horizon as well. Yes?
I'm curious to know how you got the money from the Canadian Space Agency.
Well, that's a good question.
Watch the Northern Lights? Or?
Yeah, no. They're actually interested in the soil. So they launched a couple of new satellites. Well, the RADARSAT 2 is one, and then there's also the mission that they're working with the European Space Agency. So they want to use a microwave to map the soil moisture, and then they want to have a subarctic site. So they're funding our work just so that they can get good data on soil moisture for their satellite calibration. Yeah. Oh, yes.
There's also precipitation change, like more evaporation and more precipitation as well.
Yeah. So when we looked at precipitation in a really broad brush, in a way, just looking at annual total precipitation, there doesn't appear to be a change. And then evaporation is another story, but we don't think there's a major change in evaporation. But what's changing, it appears, is the pattern of precipitation, where it seems like we're getting bigger storms, even though the total annual amount is not changing. So that might have something to do with the fact that we're getting lots more runoff these days from these river basins.